Hello, this video is an introductory guide on microcontroller programming to interface with the BQ769X2 family of battery monitors. The purpose of this video is to demonstrate steps you would generally take when designing a new battery management system and then guide you through the provided program. First, I will cover an example list of requirements for the device to show what features you may need. Next, I will cover the steps to set the settings of your device in BQ Studio. BQ Studio is included in this tutorial because it will help show the transition to programming your microcontroller. It's strongly encouraged to watch the introduction of this device working with BQ Studio before proceeding. Lastly, I will cover the starter code we are providing to assist you in beginning your own software development. For this tutorial, I will be using a BQ76952 EVM, BQ Studio, and a general code editor. As for the microcontroller, we have tested this with a couple of options that work, so it is up to you to choose which microcontroller you would like to use. Links to the tutorial on BQ Studio, where to download BQ Studio, and a link to the starter code are provided below. Getting started, we will look at an example list of requirements. In terms of the features, we would first like the regulators to remain on in deep sleep mode. Additionally, we'll need to enable the pre-regulator and enable regulator 1 to 3.3 volts. For our multifunction pins, we would like to have a way to manually turn off the charge and discharge FETs, as well as enable the FETs. Next, we'll want to enable the alert pin to be used as an interrupt. As for our thermistors, we want the TS3 pin to be used for the FET thermistor, and TS1 and HDQ pin for the cell thermistor. Additionally, we will need to configure the device to work with 16 cells for our 16-cell battery pack. Next, we'll want to enable our protections, such as cell overvoltage, cell undervoltage, along with their thresholds and delays. We'll want to read the cell voltages, current, and temperature measurements when updated. And then lastly, allow cell balancing in relax or charge states. To dive a little deeper into the requirements, here is a list of the specific protection thresholds. We will be using these in BQ Studio as well as the microcontroller code. Additionally, I'd like to point out that the values you see on screen may not be the values you see in BQ Studio. For example, for our overcurrent and discharge, it says 20 amps. However, current is calculated based on the voltage across the sense resistor. So for the sense resistor of value 1 milliohm, our threshold value needs to be 20 millivolts. Moving into BQ Studio, the first thing we want to ensure is that we're in Advanced Views mode. This can be found at the top left in Window Preferences. We'll want to have the Advanced Views selected and then Apply. Next, coming into the Data Memory tab, you'll find a full view of all of the available registers you can change. For our list of requirements, we'll start with the Settings tab here on the left. The first requirement is to have the regulators enabled in deep sleep mode. This can be found in the Power Config register. By clicking on it, you'll have a full view of all of the available bits. We're interested in Deep Sleep LDO shown here. By hovering over it, you can see the full description saying to leave regulator 1 and 2 in present state when in deep sleep. Next, I want to point out the wake speed bits here. This is not a feature in the list of requirements, but a recommendation to set this to 00. This is to change the rate at which the Coulomb counter ADC operates. We found a bug when it's set to 10, which is the default, so setting it to 00 is recommended. We'll write to data now. Notice here that the value changed and is highlighted. Keep this value hex2D80 in mind as we move towards the microcontroller code. Next, we'll continue down our list of requirements, first by enabling the pre-regulator, shown here, and then enabling regulator 1 to 3.3 volts. Again, we can hover over the bits to find the setting that describes what we want to set it to. In our case, setting 6 will set it to 3.3 volts. Next, we'll go over our multifunction pins, starting with the DFET off pin. Here, this can be configured to turn off both the charge and discharge FETs manually. For our alert pin, we'll want to set this up to act as an interrupt for our microcontroller. And then for our thermistors, we have TS1, TS3, and HDQ to work on. Here you can see TS1 is set by default to measure the cell temperatures. So we'll set the HDQ pin the same. However, for our TS3 pin, we want to configure this to measure FET temperatures, so we'll set that accordingly. And lastly, in the configuration section, we have the vCell mode. Here you can see it's being set to 0000. There are a few registers when set to 0 actually set it to the default value, in our case 16 cells. For your system, if you are using fewer than 16 cells, you will need to set these interconnects accordingly. Moving down our list of requirements, we next have our protections. For enabled protections A, we want to set the bits that we're using. So, overcurrent and discharge, overcurrent and charge, cell under voltage, and so on. For our enabled protections B, we want to set all of the temperature protections we intend to use. The next register we're interested in is the default alarm mask. One of the requirements is to read cell voltage, current, and temperature when a measurement is updated. The microcontroller will know when to read the cell voltage, current, and temperature when the alert pin goes high. This can be set with the full scan and 80 scan. Here you will see that a full voltage scan is complete, so then the full scan bit will go high, and so will the alert pin. And then last on our list is the allow cell balancing in relax and charge states. So as we go down, we'll see the cell balancing configuration section here. So we'll want to set these for relax and charge. One last thing, if we look at the manufacturing status init, here we can see that there's a FET enable bit. When using this, we'll want to either set this bit or provide the FET enable subcommand to the device so that they can enable the FETs. Next, we'll now move to the Protections tab here on the left. Here in our Protections tab, we have all of the protections and their respective thresholds, delay, and recovery. We'll start off our protections requirement list with our cell under voltage. Here you can see the threshold is being set to 50 times the unit of 50.6 millivolts. This will give us a value of 2,530 millivolts. Keep in mind, these units may not be conventional units. If we change this to 49, we'll get close to our required value of 2,480 millivolts. Next, as we move to our cell over voltage, we have 86 for our threshold being multiplied by 50.6 millivolts, giving us a value of 4,351 millivolts. By setting this to 85, we'll get close to our required value of 4,300 millivolts. Next, we have our overcurrent and charge. Here, we want a threshold of 10 amps, so we can set this to 10 millivolts for our 1 milliohm resistor. Similarly, we have our overcurrent and discharge being set to 20 amps, so we'll want to set this to 20 millivolts for our 1 milliohm resistor. Next, we have our short circuit and discharge. Here you can see there's no units, but if we hover over the threshold, you can see it's being set by a setting with the description. Here we want 100 amps for our threshold value, so we'll choose setting 5 for 100 millivolts for a 1 ohm resistor. Now that we've covered our voltage and current protections, we can move now to our temperature protections here. As you can see, we have a threshold for our over temperature and charge of 55. This matches our protection requirements list already. And as we look further down, you can see that right now all of the default values match our requirements list, so we don't need to change these. With that, we can now transition into our microcontroller code. Moving now to the code portion of this tutorial, I'll provide a comprehensive guide of the software resources we are providing to help you get started interfacing with BQ769X2 battery monitor. We will first start off by going over the initialization function. This is equivalent to setting the data memory registers in BQ Studio. One thing to note is that BQ Studio simplifies the data memory process by implementing two key steps internally. This is to enter config update mode and exit config update mode. You can see here the first line of code is to enter config update mode. This is done using the command subcommands function and sending the subcommand set config update. After this, you'll be able to change all of the registers as per your requirements. One thing to note is that you'll see predefined functions such as command subcommands and BQ769X2 set register. You don't need to worry about the details right now, as I'll cover those functions later in the video. Now that we've entered config update mode, Much like BQ Studio, we'll go down our list of requirements, starting with enabling the regulators in deep sleep mode. This is done with the power config register shown here. We're using BQ769X2 set register function with the parameters power config, which is the data memory address, hex2d80, which, if you remember, is the same value we had changed in BQ Studio, and lastly the parameter of 2, indicating the length of the data in bytes. Next, as we go down our list, we have our regulator 0 to enable the pre-regulator. Then we have our regulator 1, 2 to configure regulator 1 to 3.3 volts. Keep in mind these are the same values we had used in BQ Studio. Next, for our multifunction pins, we have the DFET off pin being set to control both the charge and discharge FETs. We have our alert pin to act as our interrupt. We have our TS1, TS3, and HDQ pins being set to their appropriate measurement types. We have the V cell mode being set to 0, 0, 0, 0. Remember, this is actually the default value, so this line of code is not necessary. However, we've included it for example's sake. Next, we'll go through our enabled protections. We have enabled protections A being set to the value hex BC, which enables these bits right here. We have the enabled protections B, which is being set to hex F7, which enables these protections here. We have the default alarm mask, which enables the full scan and 80 scan bits. We have the balancing configuration register being set. And lastly, we'll cover our protection thresholds, starting with our cell under voltage. Here you can see that it's being set to hex 31, which is equivalent to 49. Next, we have our cell over voltage being set to hex 55, which is equivalent to 85. And then we have our overcurrent in charge being set to 5. Notice here, this isn't the 10 millivolts we had set previously in BQ Studio. That's because internally there are units of 2 millivolts. So by setting it to 5, we're actually setting it to 10 millivolts, which fulfills our requirement of 10 amps. Next, we have our overcurrent in discharge being set to hex 0A, which is equal to 10. Again, this has the units of 2 millivolts internally. So that sets it to 20 millivolts, which is equivalently 20 amps across the sense resistor. Next, we have our short circuit in discharge threshold being set to hex 05. Remember, this is setting based, so by choosing hex 05, we are choosing our threshold as 100 millivolts across the 1 milliohm sense resistor. The last two registers we are setting are the SCD delay and SCD latch. This is to offer more examples on how to set your registers. Lastly, the initialization function is completed with the exit config update command. As you may have noticed, within the predefined functions, one of the parameters you use is the data memory address, such as CUV threshold or COV threshold. These are defined names linked to their numerical address in the included header file. If we look to the left of the screen, you'll see I have the header file open as a way to quickly reference any address I'm interested in using. If we dive deeper into the contents of the header file, you'll find definitions for all of the available data memory registers. Additionally, in the comments section, we've included the notation for how the Technical Reference Manual, or TRM, refers to the addresses, so you can quickly search for the details. Next, I will scroll quickly through the data memory registers to show you that the header file also includes definitions for all of the direct commands, subcommands, and command-only subcommands. These can be used in other predefined functions I will cover next. As mentioned previously, there are predefined functions available for you to use that simplify communicating with the battery monitor. To preface these functions, I'd like to go over the global variables you will commonly use with the functions. First, there is the RX data array. This is used in several communication functions to store received data from the monitor. Similarly, the RX32 byte array specifically stores data from the subcommand read function. This is 32 bytes long because the microcontroller is reading from a 32 byte long data buffer from the device. Next, we have a cluster of variables related to device measurements. This includes the cell voltage array that stores the cell voltages when read, the temperature array that currently has 3 elements but can be adjusted to your own needs if you are using varying amounts of thermistors, the stack, the pack, and the LD voltage variables, and lastly, the pack current variable. As we continue down the variables, keep in mind the type of data each one is. For example, the temperature variable is an array of float-type data which differs from the unsigned 16-bit type for the cell voltage array. The next cluster of variables pertains to the reading of different status registers. The alarm bits variable is used to store the result of reading the alarm status register. We then have the value safety status A, B, and C variables, which store a decimal representation of the respective safety status register. These can be used to broadly determine if there was a protection triggered. Similarly, the value permanent fail status A, B, and C follow suit. The FET status variable shows the states of the FETs, and lastly, the CB active cells represents the active cells and cell balancing. This variable is not used, but included as an example. Next, we have our fault flag variables. These are used to indicate the state of the protections such as cell under voltage and cell over voltage. These are read from the safety status A register. With these flags, your microcontroller can make independent decisions to further control your system. The last variable is the protections triggered indicator. This indicates whether a protection or protections has been triggered. We then have the load detect status bit, which represents the state of the load detect pin. This is not used in the example code. Next, we have our 4 FET states. The variables are updated when you read the FET status register, indicating which FETs are active. And lastly, we have our accumulated charge variables. This includes the integer, fraction, and time portion. As noted, these are used in the BQ769X2 read pass Q function. Now that we've covered the global variables, we can go over the included functions. I'll separate the functions into 2 categories, the communication functions and the example functions. We'll first go over our communication functions. Note, for the video example, we are communicating with the battery monitor via I2C protocol. The first 2 functions I'd like to cover are the I2C write-reg function and I2C read-reg function below. These functions are important to understand because depending on the microcontroller you use, you will need to adjust these functions to fit the appropriate way to communicate with the monitor. In this specific example, we are using an ARM-based microcontroller that has an included hardware abstraction layer, or HAL, library to assist in sending I2C communications. We will also provide a couple of different microcontroller examples and may have more added in the future. Furthermore, if you'd like to learn more on how these functions were developed, I'd recommend reading through the software development guide on the product page. Starting off with the I2C write-reg function, the parameters include the register address that you are writing to, the pointer for the register data, and the count, which indicates the number of bytes you are sending. For the register address, you would typically write hex 3E for the initial write for subcommands and direct memory. You would then need to write to register hex 60 for the checksum to ensure the data transmitted was correct. Again, the details are further explained in the software development guide, but we will also visit this concept in the specific communication functions. The register data that you send to this function includes either the data memory register or the subcommand and the respective data to be passed. However, for direct commands, you would only send the data. Moving further into the function, I will first describe the else condition here, as this is simple. This example uses the HAL I2C memWrite function from the HAL library. The parameters are a special I2C handle type def variable specific to the microcontroller, the device address, which is hex 10 by default, the register address passed to the function, 1, which is the register address size in bytes, the register data passed into the function, the count number passed, and lastly the timeout duration, which we have selected to be 1000. Next, moving back up, you will see that this section is conditional on if you have CRC enabled. If enabled, you will need to change the defined CRC mode macro to 1 to enter this section. In the first part of this section here is where the CRC for the data sent is calculated. The second part of this section is similar to the else conditional section by using the HAL I2C memWrite function. The major differences are the data that is being sent, which includes the CRC bytes, and the adjusted count. I want to reiterate that you need to adjust this line and this line based on how your microcontroller addresses I2C communication. Once you've made the adjustments for your microcontroller, these and the later functions should generally work. Moving now to the I2C read-reg function, you will notice that it is very similar to the I2C write-reg function. Again, the else conditional is using a HAL function, this time it being the HAL I2C memRead function. The input parameters for the I2C read-reg function are the register address, here, which is hex 40 for subcommands, and the direct command itself for direct commands. The reg data pointer will either be the RX32 byte array for subcommands or the RX data array for direct commands. This is where the data is stored once read from the monitor. The count will either be 32 when using the RX32 byte array or 2 for the RX data array. Within the CRC mode section, the order is flipped compared to the write function. The first part is to use the HAL I2C memRead function to read from the device. Then the second part is to check the CRC to ensure the data is correct. With that, we can move now to the primary communication functions you will often use in your code. Starting off, our primary communication function is the BQ769X2 setRegister function. You will recognize this function because we used it in the initialization function covered at the start of the code portion. Remember, the input parameters are the data memory register address, the data memory you intend to write, and the data length in bytes. At a glance of the whole code shown here, you can see that there are different cases for the 3 varying data lengths. It is also important to note that you provide the correct data length based on the register size, as writing hex 0000 is not the same as writing hex 00, and may cause you to write over memory unintentionally. At the top of the function here, you will see a block of code that formats the TX-reg data array. This data array is sent to the I2C write-reg function previously mentioned. The TX-reg data array is formatted for little endian, or least significant byte first, as per device definition. You can see here that the LSB of the register address is input into the first element, and the MSB here is put into the second element of the array. Subsequently, the LSB of the register data is input into the third element of the array. Looking now at case 1 for 1 byte of data, you will see that because the TX data array is fully prepared, we can use the I2C write-reg function to send it to hex 3e. The next line is a delay to wait for the information to send. This delay function is in units of microseconds and is also microcontroller dependent, so the function itself would need to be adjusted for your own system. Additionally, the value of 2000 microseconds or 2 milliseconds is partially arbitrary. However, we have found that this provides ample time for the microcontroller to write to the device. By delaying for less time, you may risk not writing the register properly. The next line of code calculates the checksum for the reg data array. The checksum formula is to add all of the bytes together and then invert it. Additionally, in the buffer, you'll need to include the combined length of the register address and data. In case 1, it's equal to 5. And lastly, you'll need to write to hex 60 the TX buffer. Cases 2 and 4 follow similar processes. The key differences are that for case 2, you will need to write the most significant byte to the TX reg data array, and for case 4, you will need to write the rest of the data bytes in little endian format to TX reg data array. Furthermore, the count numbers when using the I2C write-reg function and checksum functions were adjusted to match the size of the array you would be sending. And lastly, the combined length of the register address and data included with the TX buffer was updated accordingly. Now that we've covered the BQ769X2 setRegister function, we can move now to the command-only subcommands function, known as command subcommands. Looking at the command subcommands function, you will see that it is simple because the input parameter is only the subcommand, such as setConfigUpdate or exitConfigUpdate. All that this function is doing is formatting the transfer array, then writing the array to hex 3e, where the monitor will then operate based on the command. Next is the subcommands function. This differs from the command-only subcommands because there's data associated with each command, whether it's to read the data or write data. Notice that the input parameters are similar to the BQ769X2 setRegister function, but the last input here is type instead. This input can either be the defined macros R for read, W for write, or W2 for write 2 bytes. Again, we will need to format the transmit array TX-reg in little endian format. After this, we have the 3 conditional branches. For the type R, read, you would send the subcommand to hex3e, then you would read the address hex40, and the RX32 byte array will be populated with data. Remember, the RX32 byte is a global variable, so you will be able to read the data after you call this function. Additionally, not all subcommand reads have 32 bytes of data, so you will want to make sure you only read the bytes of data you are interested in. When using the read type, the data input parameter does not matter. However, I stick to putting 00. Another use case for the subcommands function type read is to read back the data in the data memory registers. For example, the power config register address is hex9234. By sending this address instead of a subcommand in the command parameter with type R, you will be able to read what the data stored in this register is. Next is the write type. This is exactly the same process as the BQ769X2 setRegister function, case 1. Likewise, type W2 is the same, but with 2 bytes of data being written. We can now move to the last communication function, the direct commands function. This function is another simple function with the same input parameters as the subcommands function, the command, the data, and the type. Again, the transmit array is formatted, then there are 2 conditional types, read and write. For the read type, notice that you are reading from the command address itself, shown here. The data is then stored in the RxData global variable to be read after this function. For the write type, you write the data to the command address, shown here. With that, we've now covered all of the communication functions, and we can now move to some provided example functions. The first example we'll go over is the BQ769X2 read fet status function. You can see here the first line is to use the direct command function to read the fet status register. The RxData global variable is then used to differentiate the status of the different fets. For the fet status variable, the data from the fet status register is concatenated into a single 8-bit number. For each of the fet variables, we are doing a bitwise AND with RxData and its respective bit placement. We then shift the bits accordingly to have the state be represented as 1 for on and 0 for off. These allow the microcontrollers to keep track of the fet states and may even use this information to run a specific operation. The next example function we'll cover is the BQ769X2 read safety status function. Again, we are using the direct commands function to read the safety status A register. From this register, we can distinguish which faults are active. In this example, we've chosen to highlight the undervoltage fault, overvoltage fault, short circuit in discharge, and overcurrent in discharge faults. Additionally, we've included this example to read safety status B and C. This is to provide a holistic look at the protections so that we can set the protections trigger variable if any protections are active, shown here. Next, we will take a look at a few of the measurement functions, starting with the BQ769X2 read voltage. This takes in a measurement command, such as cell 1 voltage, and reads it using the direct commands function. Then, if the command is for any of the cell voltages, it will return a concatenated value from the function. Keep in mind the value reported is in millivolts. If, however, the command is for stack, pack, or LD voltages, then it will multiply the concatenated value by 10, because the native unit of these measurements is 0.01 volts. Next is the BQ769X2 read all voltages function. This was included to iteratively read all of the voltages to reduce the number of lines you'd have to write. What this function is doing is it takes the command cell 1 voltage, which has an address of hex 14. It will then use the BQ769X2 read voltages function and then place it into the cell voltage array. It will then increment the cell voltage holder by 2 to go to the next command, which would be hex 16. Once it goes through all of the cell voltages, it will then read the stack voltage, the pack voltage, and then the LD voltage and place them in their respective variables. After the read all voltages function is the BQ769X2 read current function. This will use the direct command function to read the CC2 current value and then return the value. Lastly, for the example functions is the BQ769X2 read temperature function. Here you can see it's taking in a command, reading the command with the direct commands function, and then finally returning a float value. In the last portion of this video, I'll cover an example main function we've provided to show you how you might use this code. First off, much of the code at the beginning, shown here, is microcontroller-specific initialization features. As we move down the code, you'll see a block with familiar function calls, such as the command subcommands that resets the device, and the BQ769X2 initialization function. Notice we've also included a call to enable the FETs here. And then lastly in this block we have a disable sleep for the purposes of testing the measurement capabilities of the device. You will generally not need this for your final system. Moving now into the main while loop. The brief description of this function is to read all of the voltages, pack current, and temperature when new measurements are available. Additionally, we've included a protection indicator conditional that for our example will turn on an LED on the microcontroller when a protection has been triggered, and only turn off the LED once the protection faults are cleared. Diving into the details, you can see we are first using the BQ769X2 read alarm status function to retrieve the alarm bits. If the alarm bits indicate that the full scan is complete, then the microcontroller will enter the branch and read all of the voltages, the pack current, and the temperature. The final line of the branch clears the full scan bit to wait to be enabled when another measurement is complete. Next, we are checking if the safety status A, B, and C bits are active. If so, then the microcontroller will turn on the LED. If the safety status bits are not active, then the code will jump to the else branch, which will only turn off the LED once the safety status registers don't have a protection triggered. With that, I hope we've provided you with enough resources to get started programming and interfacing with the BQ769X2 family of battery monitors. Thank you.